Hi, I'm Chris Covington.
Hello, I'm Jameka Hicks.
And I'm Lucas Wingo.
The purpose of our project was to design a battery-powered mobile device that is small enough to fit in one's pocket.
This device records sensor data from two sensors, one that records acceleration and the other that records direction, like a compass.
It can recognize other mobile devices and wirelessly communicate its data to a computer, which allows you to look up your progress on a web page.
Our 3-volt battery-operated device allows users to keep track of their movements throughout the day. By performing specific actions such as running, jumping, or spinning around, the user earns achievements, which are awarded upon upload of data to the base station. This device is also able to communicate wirelessly with other mobile devices of its kind, as well as the base station.
This is the board I designed. It has all the components needed for our mobile motion sensing device. It has two PIC 18LF2680s. One is for the MyWi and SPI protocol, and the other is for the sensors using the I2C protocol. There are also two reset pins on the board that allows for easy resetting of the PIC if any hardware issue occurs. Okay, here's the accelerometer and the magnetometer, the two sensors on our board. Okay, the next component on the board is the MyWi chip, which is here. The MyWi is important in our design because it allows for communication between the base station and other devices. Because our board is battery operated, we had to have a battery holder. It holds a 20mm 3-volt 2032 battery. The board is equipped with a piezo buzzer, which allows the user to be alerted when another device is within range. There are a total of 7 LEDs on our board. One LED is for power, and the other 6 LEDs assist in debugging. In various places throughout the board, I have placed jumpers and shunts, which allows for easy measurement of the current and calculation of power consumption.
This PIC is the sensor PIC. It communicates over I2C to the accelerometer and magnetometer. Both of the sensors are 3-axis devices. With the accelerometer, I cut it up into the vertical axis for jumping and the horizontal axes for running. With the magnetometer, I ignore the vertical axis and just pay attention to the horizontal ones for turning. To tell if someone has turned around, I check if the magnetometer has had readings in all 4 quadrants of the horizontal axes. To see if someone has jumped, I see if the X in positive direction reading has reached a certain threshold from the accelerometer readings. To see if someone has run, I check if the sum of the Y and Z readings are above a certain threshold. Once an achievement has been detected from one of the sensors, I send it over UART to the MyWi PIC.
What's up? How's it going? I'm Lucas Wingo. I'm the MyWi and Spartan guy. Also, the science guy. Can I be the science guy?
Sure.
I'm the science guy. In order to make the design as flexible as possible, we decided to have the configuration for the mobile device and the base receiver be the same for the breadboards. And this is the MRF24J40. It's the transceiver we used during our project. It communicates wirelessly up to 400 feet, and it operates with a 2.4 to 3.6 voltage. It's low power, for transceivers. Alright, the transceivers in our project communicate using the MyWi peer-to-peer protocol. This lets them handle meeting new devices in real time with ease. Instead of having to establish connections when they start up, they can establish them at any time. It also allows them to exit and cancel connections since they will be moving in and out of range of other devices frequently. Communication involves sending connection requests periodically between devices in order to identify when a new device has come within range. When a device has recognized that a base receiver is within range, it uploads its data in order to be displayed by the Spartan board through a web page. The Spartan board displays the data that has been uploaded to it in a form that's easily understood in the form of a web page. The web page displays whether you have earned certain achievements that are achieved depending on the sensor data received by the mobile device. The web page we're using currently displays the achievements that you have earned and haven't earned. The achievements you have earned have congratulations in front. For instance, right now, the mobile sensor that is within range has accomplished the running task, as well as it has made a connection and found the base.
The sensor data acquisition checks for various error conditions, but the error conditions I could think of were all showstoppers. So with these assertions, it can tell what the problem is, and it notifies via a debug message what they are, but the program will have to be reset under proper operating conditions for operations to continue.
Since our implementation of the MyWi uses a peer-to-peer protocol, there is no harm in losing a radio connection between mobile devices. Wireless connections can be added and dropped at any time from the peer list of the device easily. In order to make sure that the MyWi device is not in a bad state at any time, it is reset periodically when no devices have been detected within range. Making sure that there are no devices within range ensures that no connections are terminated pointlessly.
So some of the limitations of our implementation on the sensor side are that the correct orientation matters and there is no tilt compensation.
Something good about the MyWi is that it works just as fine in your shirt pocket as it does sitting on a desk. However, the wireless signal strength varies greatly depending on the environment around the user. Depending on the types of walls and objects around the user, such as metal blockers and elevators, the device can be able to transmit only 5 meters away, or, and depending on a good environment, up to 20 meters away.
To ensure the reliability of the I2C subsystem, I periodically check if the system has failed to transition within a given amount of time from one state to another. If it's stuck, and in practice this would happen on the stop condition, then I have a timer callback function that will push it into the next state and reset the entire MSSP on the PIC.
When powered from a stable power source, the MyWi transmissions are very reliable, and I've had them running for up to 60,000 packets, and it doesn't even fail after that amount of time. So,
however, when running on a battery supply, the 3-volt 2032 battery that we chose for our design, the board was very prone to brownout.
Brownouts cause the MyWi chip to enter strange states and possibly, be reset without the PIC microcontroller knowing that it has been reset, which means it can't actually talk to the MyWi chip anymore. So the brownouts, even if it happens on one component, it can lead to the whole system failing catastrophically. In terms of reliability, the base station, which is made up of a breadboard and the Spartan board, was very unreliable. It often, when it started, it would work correctly. However, periodically it would fail after around 15 minutes for unknown reasons, possibly because of the network thread interfering with the I2C thread, leading to hanging in the on the I2C bus. However, as has been said, it works correctly when it was after a fresh restart.
So one potential improvement would be to use one PIC microcontroller to communicate over I2C and SPI. Using a PIC with two master synchronous serial ports would allow this, and it would reduce the footprint of our hardware on the printed circuit board. This wouldn't affect very significantly the power consumption, however, because while we would have just one PIC drawing power, it would sleep less often, and in sleep mode, the power draw is negligible. One potential PIC improvement would be to compensate for the tilt of the board. While the current algorithms only work in the upright position, compensating for tilt would allow the device to still successfully detect jumping, running, and turning around in any configuration.
In order to improve the running time of the mobile device, a battery with more milliamp hours, such as those found in cell phones, could be used in the design. For example, the 3-volt quad cell battery that we are currently using has 220 milliamp hours. However, this 3.7 lithium-ion battery found in cell phones has 1,300 milliamp hours. Another idea would be to use a rechargeable battery in order to prevent unnecessary cost replacing batteries. Although the change in size is significantly larger than the quad cell battery we are currently using, increasing the footprint, overall it would be more cost efficient. Also, a higher voltage battery could be used so that a voltage regulator may be added to the design to decrease the likelihood of brownout. This improved stability would, however, decrease the battery life.